Hello and welcome to our MSc 4793 presentation. My name is Gavin Garland, and I, along with my group members, Simon Paulsmeyer, Alden Neville, and Braden Kirsten, will be exploring the use of composite materials in Formula One racing. Formula One is known as the pinnacle of motorsport and features the quickest cars in any racing series. Each year, the 10 teams are tasked with constructing an open-wheel, single-seater car that meets the regulations set out by the championship's governing body. Once they've built the cars, they then race at tracks all over the world to determine who is the best constructor and best driver. The goal of each team is to build a car that is faster than their competitors while also keeping the drivers safe in the event of a crash. Motorsport, and specifically Formula One, seeks to push the absolute limits of engineering in order to increase speed. And due to this, many innovations in manufacturing, design, and safety are first seen in competitions such as Formula One, before they trickle down to consumer products like road cars. In addition, F1 has an incredibly high rate of development, with teams designing, manufacturing, and deploying parts all throughout the season. Every inch of an F1 car is fine-tuned and optimized for speed, and even just a few kilograms in weight reduction can result in the car completing the race 30 seconds quicker. For these reasons, starting way back in 1980, teams have been making use of carbon fiber composites when building their cars to cut down on the weight, while still maintaining their durability. Composites have also allowed for improved safety devices, such as crash structures to absorb impacts and monocoque chassis to protect the driver. The complex geometry afforded by composites has also allowed for intricate aerodynamic design, which has greatly improved performance. In this presentation, we will examine how composites are utilized and manufactured in Formula One. But first, we want to give a brief introduction to the components of a Formula One car.
I want to quickly introduce what a Formula One car actually looks like. On the screen here, you can see the McLaren Formula One car from 2021. Starting at the front, you can see here the front wing. Behind it, the two front wheels that ride on the suspension. You can kind of see here. It's an open wheel car, so you can actually see the suspension members pretty well. You can see the driver sitting here, and their legs kind of go like this, like up here to the front. Across the driver's head, you can see the halo, which was a recent addition to protect the driver's head. The car flips over, or another car drops on top of this one. Next to the driver is the side pod area, which in this year featured barge boards up here, which are just basically there for aerodynamic conditioning. And behind the driver is where really the race car is. So there's the engine and the gearbox, as well as the hybrid components such as the electric motor, the power generation, and the big battery. And then here in the rear, you can see the rear wheels, which are the ones that are driven, and the rear wing. What's really interesting about this is about 85% of the volume of the car is actually made of carbon fiber, and about 70% of the weight is carbon fiber, which is why it's so applicable to this class. One specific component I'd like to highlight is the monocoque that's used in the cars. So in the past, the structure of the cars really looked like this. It was welded steel tubes that made up the whole structure. This was pretty heavy, not the safest option for the drivers, and in a crash, the whole thing could bend, basically destroying the whole chassis and have to rebuild. In 1981, McLaren introduced the MP41, which was the first car that had this monocoque. You can see it down here. It's basically one large carbon fiber part. The driver sits inside it. It's also called a tub sometimes, kind of like a bathtub because you really do sit inside it like a bathtub. And this is one large composite part. And this offered huge weight savings compared to the old steel frames, as well as also being much safer. The car manufacturer did not have a lot of knowledge with composites, so they actually hired Hercules Aerospace out of the US to help them with this, since they had some more experience with it, building fighter jets and such. This was laid up by hand, and it's a pre-bicarbon composite. It was made with one large male mold, and you can kind of see how they constructed the mold here in the top. They milled these individual sections, connected them together, and then did one big layup on top of it, and then had to destroy the inner mold to get out the final part, basically. This worked out really well for them, and the car dominated that season. But there was some problems with it. For example, since only the inside surface was well defined by the mold and the outside surface was pretty rough, you had to add bodywork around this, such that the outer surface would be smooth for the air to flow over without creating too much drag. That issue was solved 2 years later by the Ferrari team. They were the first team to implement a female mold. What they did here is they basically, out of foam, milled the inside of the monocoque. On top of the foam, they laid up, using carbon fiber and fiberglass, a mold, which looks something like this down here. And then on the inside of that mold, they laid up the final carbon fiber part. The advantage of this is that now the outside of the part was very, very smooth, which is good for aerodynamics, of course. And so that way you could just paint the outside of the monocoque, and that was your car basically. So what we're seeing here around the driver is actually the monocoque straight away. There's no bodywork around it, which is obviously great for mass saving. A similar technique is still used today, although a bit optimized. Down here you can see the 2014 Caterham mold for their monocoque. You can see in the back the foam pattern that was used for this. Basically, on top of this pattern, in multiple sections, carbon fiber is laid up, and you can kind of see how they connect here with these long pleats. And so they make these multiple sections, connect them all, and now you can lay up on the inside of this mold to make your final part. This is all done by hand, which is very tedious, of course, but since there's only so many cars and monocoques made every year, it doesn't really make sense to develop any tooling and any automated tape placement for this. It just doesn't work out financially for the teams. All monocoques are made of carbon fiber and epoxy. This is just because that's really the most dominant material that teams have found, and it's just the strongest, really. In the middle, though, oftentimes the aluminum honeycomb is added. You can kind of see a nice cross section down here. So on the outside is about 10 layers of carbon fiber, about 1 millimeter. Then a thick layer of honeycomb is added, and then on the inside another 10 layers or so of carbon fiber. This is the most efficient way teams have found to make the monocoque as strong as possible while still being very light. And very light it really is, only 35 kilograms for the whole monocoque. It's a pretty large part, and it's super strong, as we'll see in a minute. So I'm really impressed every time by how light these things are. I want to quickly go through the process of how it's made in the modern day. So in a big 5-axis CNC machine, the teams mill the pattern. So you can kind of see it here. This is not for a Formula One car, but a similar process is used in this application. They mill this out of foam and then lay up on top of the part with fiberglass and carbon fiber the mold. And then inside the mold, they lay by hand the carbon fiber. I already mentioned why. And so when laying up the carbon fiber on the inside, after placing those first 10 layers or so, whatever they have come up with in their layup schedule, it goes into the autoclave. Of course, the teams have very modern autoclaves just to get that extra bit of performance out of the part. After going through the first curing cycle, they take out the part and then attach the aluminum honeycomb. To do that, another layer of epoxy is added, and then the honeycomb is added on top of the epoxy. It has to get cured again now to attach the aluminum honeycomb to the carbon fiber. So into the autoclave it goes again, gets cured once more, and comes back out. And then finally, the outside / inside layer of the monocoque can be added, and again it goes into the autoclave and comes out, and that's your part done. Oftentimes the teams will have to go in and trim some parts, maybe sand here and there to make it extra smooth, but that is the basic process. And in the end, what oftentimes does happen is it has to go through another milling cycle. This is needed because precise location on the layup is oftentimes hard to define in the layup schedule. For that reason, after laying it up fully and curing the part fully, it is taken into a mill, which then oftentimes defines the locating features. For example, the suspension hard points, where the engine attaches, and so on. I want to quickly just highlight how effective these monocoques have been. The first year that they were used in 1981, after the first shunt, it was a big one. It was a big crash, and all the engineers were pretty worried. But then when they got to the car, the driver got out without a problem. Really, the whole engine was broken, everything was broken, the engineers were worried, but the driver got out and the monocoque was untouched, basically. And it continues to be that way. I put a few pictures here of a crash in 2007 that Robert Kubica had. You can see the car gets obliterated after it hit the wall at 300 kilometers an hour. But down here you can see the monocoque, and it's just fine. You can see here at the front, his feet are well protected still. The front totally broke away, which is the crash structure that we talk about later. But he himself is protected fully, and he did not get injured here at all. Even though this is a really scary crash that had G loading of up to 75 Gs, he was ready to go 2 races later. Another safety change that was made is adding some layers of Kevlar. In 2013, a suspension member punctured the monocoque side and basically hit a driver's legs from the inside. After noticing that, the FIA, the governing body, introduced the rule that Kevlar members or Kevlar layers had to be added into the monocoque such that puncturing is much less likely. Now suspension members can't ram through the monocoque anymore, and neither can any other parts that are flying around on the track.
Dynamics is one of the most fundamental parts of a Formula One car, and one of the biggest points of innovation year to year. Almost every single piece of a vehicle's aerodynamic components are made from composite materials. Major components include the front wing, rear wing, side skirts, and really most of the body of the vehicle. The main goal of all of these pieces is to provide the vehicle with as much downforce as possible while keeping drag and weight low. With the amount of force that these components will need to withstand, combined with the need for minimal weight, composite materials are clearly the best option. Most of the larger components, such as the front and rear wings, are made from many separate pieces which are then bolted together. This makes replacing damaged parts or changing setups for different conditions much easier and more cost-effective. These smaller individual pieces are usually flat and panel-like with bends on either side for bolt holes. Most of these parts are made out of a mix of carbon fiber and epoxy, usually about 10 layers thick, and are created using a hand layout technique. This technique provides flexibility in the design itself, and the material used gives a very high rigidity with minimal weight. Sometimes the physical properties of composite materials, namely flexibility, can be tailored and used as an advantage. In the past, teams have created aeroelastic components such as flexible wings to adapt to the ever-changing conditions of a race and provide an increase in performance. Though composites have many advantages for Formula One, there are also many disadvantages as well. The biggest disadvantages of these components is the cost. Just a front and rear wing alone can cost upwards of $500,000 for one pair, and the car itself can cost around $15 million in total. Though these components are expensive, because of sponsorship deals, this cost is thought of as a necessity and is not as important overall. Another major disadvantage to some composite materials is the heat resistance. Certain composite materials are prone to warping or melting under high heat, or even burning under extreme high heat conditions, and this can be a major issue in certain areas of the vehicle. For example, the brakes of a Formula One car can reach up to 1800 degrees during a race, and this would simply burn most composites away.
Other important components of the car which are constructed out of composite materials are the impact structures, which reduce the impact on the driver during a crash. Force is equal to mass times the change in velocity divided by the change in time. So when a car experiences a crash and goes from a high velocity to stationary, the longer the car decelerates for, the less force will be transmitted to the driver. In order to increase the duration of the crash, impact structures are built into the car which intentionally brake gradually and help decelerate the car. Composite materials are tasked with this important job because they have a high specific energy absorption, or SEA. For example, carbon fiber reinforced polymer with a certain structure can have an SEA of 40 to 70 kilojoules per kilogram, as where aluminum has an SEA of 20 kilojoules per kilogram, and steel can only absorb 12 kilojoules per kilogram. This means that a composite impact structure can be much lighter when compared to an aluminum or steel impact structure and absorb the same amount of energy. On an F1 there are 4 crash structures: the one in the front, the one in the rear, and one on either side of the car. All of these are made up of a carbon fiber composite with an aluminum honeycomb core and are laid up in a very similar process to the way in which the monocoque was, as discussed earlier. You can see in this image here, which is a cross-section of an impact structure, this internal honeycomb structure, with the outside being the carbon fiber composite, which will crumple under load. Here we have some pictures of a test specimen of the impact structure. This here is the front impact structure, and you can see that it is colliding with the wall and crumpling under time. This is what it looks like before impact, and during impact, these pieces break away gradually and slow down the whole driver and car so that the crash is more survivable. One of the stated goals of Formula One is to pursue and develop new technologies that promote sustainability. One very interesting area where this has been implemented is use of high-performance sustainable composites. The McLaren F1 team has utilized a flax plant natural fiber in their racing seats for their drivers. You can see this in the photo. The natural fiber seat is on the right and the traditional carbon fiber seat is on the left. The natural fiber has a 75% reduction in environmental impact when compared to carbon fiber and is cheaper to produce. In addition, the plant-based fiber is biodegradable, so it doesn't produce nearly as much waste as carbon. The team was able to manufacture a seat that was as strong as the original carbon seat, while also allowing for 5 times increased vibration reduction. The one main downside to natural fiber composites, and the reason they haven't been adapted to use in the rest of the car, is that they have a low strength to weight ratio when compared to traditional materials. Teams are working with manufacturers to improve natural fiber composites so that one day they may be used as a primary material on Formula One cars and many other products. Thank you for joining us, and we hope you enjoyed our presentation.